We present an approach to rendering the ellipsoid surface of a virtual globe using GPU raycasting. Globe rendering has widespread uses in virtual globe applications and video games. Traditional approaches based on tessellation and rasterization have several drawbacks. Tessellation algorithms utilizing a geodetic grid result in oversampling at the poles. This leads to lighting and texturing artifacts, as well as inefficient view-thrusting calling. Tessellation algorithms based on subdividing an inscribed platonic solid lead to problematic triangles crossing the international date line and poles. We present a new approach to globe rendering based on GPU raycasting, which has all the traditional advantages of raycasting implicit surfaces: an infinite level of detail, trivial memory requirements, and simplicity. Furthermore, our approach drastically reduces ray misses, runs at real-time frame rates on commodity GPUs, and easily integrates into existing rasterization-based engines. Our approach begins by rendering the bounding box of the ellipsoid with front-face calling. Front-face calling ensures a depth complexity of 1 and that the ellipsoid does not disappear when the viewer enters the box. The box is rendered to invoke a fragment shader that casts a ray from the camera through the fragment's world space position. Here, ray intersections with the ellipsoid are shown in cyan, and ray misses are shown in gray. For proper shading, fragments with ray misses are discarded. For rays intersecting the ellipsoid, the intersection point and geodetic surface norm are computed and used for shading. In order to allow both raycasted and rasterized geometry in the same scene, the intersection point is transformed to derive the fragment's depth value. Here we show a raycasted globe rendered with rasterized billboards denoting cities. Next, we present two optimizations based on transforming the ellipsoid into a scaled space where its representation is spherical. From many views, especially views along the horizon, a large number of rays miss the ellipsoid, as shown here in gray. To reduce ray misses, and thus fill rate, we replace the bounding box with a convex polygon that bounds the ellipsoid from the viewer's perspective. We compute such a polygon in the scaled space. The equation that defines points on the surface of an ellipsoid can, through a simple linear scaling transformation, be represented as points on the surface of a sphere of unit radius. Correspondingly, the points which bound the front face of the ellipsoid surface, as viewed from an external point, can be shown to comprise a simple bounding circle on a unit sphere. Since the transformation between the ellipsoid and spherical representations is a simple linear scaling transformation, linear relationships are preserved in the two representations. Specifically, lines or rays which intersect the ellipsoid surface in the original representation will have a corresponding line or ray in the transformed representation which will intersect the sphere. We use the vertices of a regular polygon, which circumscribes the bounding circle on the unit sphere, in order to determine the region of the viewport where ellipsoid ray intersection testing is necessary. This viewport and line bounding polygon is rendered to invoke the raycasting fragment shader instead of the bounding box previously used. The number of vertices in the polygon allows a trade-off between CPU and vertex processing and fragment processing. We also formulate an optimized ellipsoid ray intersection algorithm in terms of the spherical representation to reduce the overhead for both missed and intersected rays. Next, we compare the performance of our raycasting approach against the performance of rasterization. With rasterization, we received 134 frames per second for a coarse mesh and 112 frames per second for a finer mesh. These are best case numbers that do not include any CPU overhead or bus traffic that would be incurred from level of detail algorithms. Our raycasting approach based on rendering the ellipsoid's bounding box ran at 94 frames per second for a full globe view and 78 frames per second for a horizon view. This approach has a constant triangle load of only 12 triangles and has virtually no CPU overhead or bus traffic. Furthermore, the surface is infinitely smooth and did not require any tessellation. Our optimized raycasting approach based on rendering the viewport aligned bounding polygon improved performance to 111 frames per second for a full globe view and 94 frames per second for a horizon view. This approach requires minimal CPU overhead and bus traffic to compute and send the bounding polygon. Here, 10 vertices were used for the polygon. In future work, we plan to compute the number of vertices required and the bounding polygon on the GPU.